1.3? Yeah. So we skipped 1.3 because section 1.3 is is a section that talks about modeling, but it doesn't solve for the differential equations because we hadn't learned to solve for them yet. So it was kind of like a preview of what's to come, but it's kind of boring. So this chapter kind of takes some of that information, at least the first order stuff, because there is a couple of second order differential equations there. But the first order differential equations, they put it back into chapter 3 because now you know how to solve for a lot of first order differential equations. So that's what we that's what we're going to cover today is we're going to take a look at some of those problems that were first introduced in 1.3, but now we can set them up and actually solve for it. And so the way I was going to do this was just to introduce some concepts and ideas, and then we'll just jump into trying to do one of those problems in from the textbook. So let's see, where's my textbook? I have to do this. Let's see if we can get the textbook this way. So there's a handful of really simple problems that we could start with the growth and decay, and you probably have seen these problems back in um, calculus or maybe even pre-calculus. Let's pick a problem here, number 5 or 6 maybe. Any suggestions? Uh-oh. All right, we have a radioactive isotope, and it decays at a rate proportional to the amount present at the time, and its half-life is 3.3 hours. So 1 gram of isotope is initially present. How long will it take for 90% of the lead to decay? And what we want to do is we want to again relate the words into math somehow. The rate is proportional to, so let's say A or P, let's say P equals the amount of lead at time T. And then has a half-life of 3.3 hours. Oh, so P of T is the decay rate, so that's P prime of T, is proportional to the amount present at time T. So we have dP dt is equal to proportional, so it's equal to K times the amount. So this is the standard differential equation that, the first differential equation that we work with, and this is the one that's most popularly used and easiest to get in pre-calculus and calculus. Um, so we know that the solution to this is, should we do the differential equation? let's pretend we're in a differential equations class and solve for this using differential equation. This is a separable differential equation. We integrate. And then we solve and put it in some fancy way. E is equal to a e to the kt, or we can use p naught there if we want. So these things usually require us to solve for k, and the information about the half-life or the information about some sort of marker in the process of the growing or decaying will help us solve for k. So the half-life in this case is 3.3 hours. And what does that mean? Half-life is 3.3 hours. So it says that half of 3.3, no, half of the amount will be gone in 3.3 hours. So let's say A was the original amount. It's equal to 1, but let's just say the original amount. And then half of A is the half-life. The half of A is half of what's left, right? And this is supposed to be equal to the amount times e to the kt in 3.3 hours. And so we can solve for this, and then we have the ln of both sides, and then you take you divide by 3, so k is equal to 1 over 3.3 ln of 1/2, or whatever. And then you put this in the calculator. See, it's negative, so it's a decay, and it does make sense that it is a decay. Right, ln of something that's less than 1, between 0 and 1 is negative. So this is a negative number, it's a decay. And then we know that 1 gram of isotope is present initially, so your P naught or your A is equal to 1 gram. And then we're all set to find how long will it take for this thing to decay to 90. So your actual function, we have the solution for this already. P of t is equal to 1 times e to the k times t. And then to try to answer their question is how long will it take for 90% to decay? So 90% of 1 is equal to 1 e to the 1 over 3.3 ln 1/2 t, and then we're solving for t. What? Oh, 90% to go away, so what's left is 0.1. Yeah. Amount remaining. All right, so we do the same thing. We do another ln, solve for this. So, and then we solve for t. So t is going to equal to, see what happened. We took the ln of both sides. We're going to divide by this. So it's ln of 0.1 divided by 1 over 3.3 ln of 1/2. And then you're going to get some number for this if you did it properly. Yeah, if we see that, the A's would cancel all the time anytime we do any sort of work. So yeah, if we're just caring about what percent is left, usually that's what they want to do, and that's how they age things. That's how they figure out how old things are. Anybody want to punch this in the calculator? Should I use Mathematica to solve for this? That's probably a little too much, huh? let's see, log 0.1. Oh, I need brackets. 10 hours, 11 hours, close to 11 hours. Yeah. Yeah, this is the natural log. Log 1. Oops, not log 1. What do I want? Log E. Log E. Yeah. It's yeah, I took a computer science what do you call those? GREs or MCATs or no? That high school thing when you get out of high school? Oh, maybe a GRE, graduate school. Yeah, I took one of those things. For math, when they do LOG, they mean the ln. And computer science, when you see LOG, they mean log base 2. And then in biology, when they do LOG, it's log base 10 because they do log stuff in biology. So LOG is log, but then in different contexts, you know, it's natural log, the log base 10, I don't know what log base 10. Sure. Oh, scientific notation. Because E is a way to do scientific notation. It's the way to denote scientific notation. No, it's not the number E. It's what? Yeah, capital E. By the way, 2.7 is like the E day. You know, there's Pi Day. So February 7th was E. So this one E, this E is your exponent. And so to the third is 1,000, right? 3 zeros. All right. So that's our little warm up. Let's get some more interesting differential equations. Let's take a look at Newton's law of cooling. Ooh, you have? The gravitational constant? Oh. Oh, I still have these little things here. too big. What happened? Oh, sorry. I'm gonna. So Newton's law of cooling is similar to the growth and decay, um, except there is an ambient temperature that this thing is going to reach. So this is applied in many different things. If you're baking a cake, you put your cake in the oven. Your cake is currently at room temperature. You put it in the oven at 350 degrees, it's going to go up, but it's not going to keep going up forever because the maximum is 350 degrees. So it's going to reach a peak, or the other types of problems that are interesting here, like in forensics, timing your time of death, somebody's time of death. And so, assuming that a regular body temperature is whatever it is, 98.6 or whatever, and then the room temperature is like 60 degrees, so your body temperature is going to cool down to 60 degrees. Yeah. Well, like I said, it depends if it's warming or cooling. So if you put it in the oven, then you're warming up, so K is positive. So yeah, I guess it could be. Yeah. Yeah, I think so. Well, it depends on the T minus TM, the difference. I don't know. We should just do a problem and figure it out. So let's see. This is the Are we here? Um, should we do something in Celsius? Not that it matters. 16? I don't know. That looks hard. 2. Yeah. Sounds good. All right, let's do this one. Thermometer taken from inside a room to outside where the temperature is 5 degrees Fahrenheit. That's kind of cold, huh? After 1 minute, the thermometer reads 55. After 5 minutes, it reads 30. What's the initial temperature of the room inside? So here, it seems like the initial temperature is like an A naught or an T naught or whatever, T naught that we're looking for. And then we're using the 5 degrees and the 55 degrees as a marker to help us solve for a few things. And so let's see if we can solve this problem. We have our differential equation. It looks like T dt 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 dt. Should we change the T? Oh, it's temperature. Let's keep it as T. kt over t times, or t minus t sub m, and then we're essentially looking for t naught, which is normally something that would be given to us. um, and the temperature outside is 5. So your your thing, the body that you have, is the actual temperature, or the thermometer. And your thermometer has a starting temperature when you were inside, and then you took it outside. And the 5 degrees here, I think, is going to be the ambient temperature on the outside. Does that make sense? So I would probably call this T sub m to equal 5 degrees Fahrenheit. And then we should probably solve for this differential equation. Now the thing is that since this is the same differential equation we've seen, we should probably know the solutions on it if we had done it. But let's do the differential equation. It's a separable differential equation, and we have ln of t minus t sub m is equal to kt plus a constant, and then t minus t sub m is equal to, we'll put the t naught here, e to the kt, and then so t of t is equal to um, t naught e to the kt plus t sub m. Is that right? I hope that's right. Oh, yeah. So T0 minus Tm. So over here, you want T, wait, do we want T of 0? Yeah, so times 0, at times 0 to equal to T sub 0. So that means this, this unknown coefficient, I guess we'll call it A for now, should equal to T naught minus Tm is equal to a e to the k times 0, which says that a is equal to t naught minus tm. So that should be t naught minus tm. Or you can, is that right? You can change it around a little bit by doing some other factoring thing or whatever. So we're looking for t naught. We don't know what k is equal to. We don't know, well, we know what tm is equal to, so we could put tm is equal to 5 degrees, and then we'll solve for the rest of this, hopefully. So we have a couple of pieces of information here. We'll say t sub m is equal to 5. We know that in 1 minute, we have uh, 55 degrees Fahrenheit. And then in, what is it, 30? 30 minutes. Oh, 5 minutes, it'll be 30 degrees. 5 minutes, it'll be 30 degrees. Okay, so we'll use those pieces of information. Let's first rewrite this with the TMs. So T naught minus 5 e to the kt plus 5. And so we'll try to solve for k or something. Maybe solve for k and t at the same time. So when t is equal to 1, t of 1 is equal to 55. So that's 55 is equal to t naught minus 5 e to the k times 1 plus 5. And then in 5 minutes, it's 30 degrees. So t of 5 is equal to 30. T naught minus 5 e to the k times 5. That's 5 minutes. So we have these two equations that we can try to solve for, and we can solve for both k and t. I don't know what the easier way to do this would be. We'll solve for t up on top. So we subtract the 5. We divide by e to the k and then add another 5. If you what? So subtract the 5 for both of them. So 50 is equal to t naught minus 5 e to the k, and then 25 equals t naught minus 5 e to the 5k. And then just eliminate the middle, the t minus whatever. So this is what? E to the, is that what we're saying? And then I suppose we can just say this is 2 is equal to e to the minus 4k. Is that 4? And then I'll take the ln and divide by negative 1/4, divided by negative 4. So k is equal to negative ln2. So ln2 is positive, this is negative, so this is decreasing, which is what we're looking for. Now I suppose we could just take this k and then plug it back to solve for t. So we'll put it into the first one. We got 55. We'll put it into that one. 50 is equal to t minus 5 e to the negative ln2 over 4 t naught. And so we'll solve for this. We get t naught is going to equal to, bring that over and we add 5, right? So it's equal to 50 e to the ln2 over 4, because when you bring that over, it turns positive, the powers, and then 5. That seems reasonable. You're inside, it's 64 degrees, and then you bring it outside, it's 5 degrees, and your temperature starts dropping. So that makes sense. What is it? Okay. Any questions? By the way, watching me solve this isn't going to help you. You have to actually do it yourself. All right, let's take a look at another type of problem. We should graph these things. Did we graph the last one? Nah. You want to do a mixture problem? No. Yeah, I guess so. I don't know. Nothing's wrong with mixture problems. So we got two different salt solutions, differing concentrations. We have a first order differential equation that says the A, they don't say what the A here is. A of T is equal to the amount of salt. And so mixtures going in, mixtures going out. So there's a change in the amount of mixture in the pot currently. So the rate of change of the salt coming in minus the rate of change salt coming out seems like it's the reasonable way to describe this particular differential equation. So let's do a problem. There's a problem here. There's actually a couple of problems here. It's kind of similar to related rates, except it's a little bit more complicated. Ooh, I better just get it from the book. Wait. Oh, I can just copy and paste the actual text part. All right, we have a tank that has 200 liters of fluid and 30 grams of salt dissolved. So that's the original amount in the tank. Brine containing 1 gram of salt per liter is going in, is then pumped into the tank at the rate of 4 liters per minute. And then the solution is then pumped out at the same rate, 4 liters per minute. So I think if we could figure out the amount going in, the amount going out, then that's really our key here, right? So let's see the amount going in. So the amount going in, well, first of all, in the beginning, we have 200 liters and then 30 grams of salt. So that's 30 grams of salt. That's your initial amount, A of 0. I don't know if that's needed in this problem, but that's the amount of salt that's in the tank in the beginning. And then we have brine coming in, so R in. 1 gram of salt per liter. 1 gram per 1 liter. These ratios and units are going to be important for us here. 1 gram per 1 liter coming in. And then the rate that it's pumping in is 4 liters per minute. 4 liters per minute. So it looks like we have 4 grams of salt per minute coming in. So that makes sense, right? The amount of salt that we have is in grams, and then the rate that we're looking at is grams per minute, the amount of salt per minute coming out. So it seems like it's grams per minute. So that looks like it makes sense. What's the amount going out? So it's a mixture of what's going in, what's already there. So R out, what's the mixture going in? 4 grams per minute. That's the mixture going in, right? And then we have the mixture that's in there right now. Well, that's just the initial part, right? So the actual amount, well, the amount is changing. So I think this 4 grams per minute plus the mixture. So I think what we actually have is the amount at some particular time t because it'll change um, in grams per liter. Yeah, for 200 liters because that's how much is in there. Wait, this isn't a rate yet, is it? Um, oh, it's still, yeah, it's going out at the same rate of 4 liters per minute. So we'll do the 4 liters per minute here. Now, now it's in grams per minute, right? 4 into 200 is what? 25 or something? What? 50? Okay. So that's our out. We have R in, we have R out. Let's see if we can write our differential equation. So dA dt is equal to R in, so that's 4 grams per minute. And then this is also grams per minute, so let's just ignore the things at this point. Minus A over 50. What kind of differential equation is this? Separable, right? You can separate it. Should we solve for this? Yeah, we're solving for this. All right, so if this is going to be separable, we need to combine it into one fraction. So let's see, we'll go back to 200. Is that 200? Right, 200 over 50 is 4. So now we can separate it. We have dA 200 minus A is equal to 50 dt 150. Oh, is it? Yeah, 150th. Um, and then we'll integrate. This is going to be negative, right? ln of 200 minus A is equal to 1 over 50 t plus constant. What should we do next? You can solve for C at this point. So we know that C. So there's different places to solve for C. You can solve for C here, or you can solve for C later. Let's solve for C later. So let's. I think if I can take the negative out, this way. Now, minus C and plus C are the same thing, so I'm tempted to just put a plus C there. What if we'll just leave a little mark here to say this is a different C from the first C that we got? Okay, and then now we'll take the ln, and then so that's e to the C1. I'll just call that A since that's, oh, I can't call that A. A naught? I don't even know if I can call it A naught. Yeah. I took the negative sign out. I multiplied both sides by negative. And then I changed this C into C1 to say C is negative C1. Oh, yes. Thanks. So I'll call it C2. E to the minus 1 over 50 T. And then, yeah. Well, I'm just calling it A. I don't know. Yeah. Yeah. Well, almost. Yeah, there's a 200. The logistic model, the 200 over there makes it not quite exactly the initial. All right, we are solving for A. So A is equal to, bring the A on the other side, it would be negative, and then change it, it'll be positive, and then this will be negative. And then, what was the initial amount again? A of 0 is 30. So we got 30 is equal to 200 minus C2 e to the minus 1 over 50 times 0. Well, that doesn't matter, 0. So C2 is equal to what? 170? And then finally, is it finally yet? Yeah, it's finally. So A of T, this is your thing, your equation, is equal to 200 minus 170 times e to the minus t over 50. Okay. Is that all they want? Yeah. So it looks like it's a logistic model, and then if you were to graph this, we should see an asymptote somewhere. Any questions? This is an increasing or decreasing function. Does it look like there's more salt being added? So there's 4 grams a minute, 4 grams a minute of salt coming in, and we start off with 3 grams. Looks like it might be increasing slightly. So let's see. So it starts off at 30, and here's your bend over here. So this could potentially have close to almost full concentration of salt, 200 liters of salt, 200 grams of salt. Yeah, not that bad. All right, that's interesting. Should we take a picture? Let's take a picture in our notes. All right, what's next? Ooh. Oh, yeah. All right, let's do some circuits. Oh, so the circuit setup. Yeah. So this is one of those examples back in 1.3 where we ended up with a second order differential equation. So this is a setup uh, for um, for that section, and we get a second order differential equation. But since we are only doing first order differential equation, we can limit ourselves to just LR or RC circuits. So let's see. Let's not worry about the circuits and the second order circuits. Let's do this one. So an LR. We spell circuits. All right, so we're just going to keep it simple here. For a series circuit containing only a resistor and inductor, the second law states that the sum of the voltage drop across the inductor and the voltage drop across the resistor is the same as the impress voltage on the circuit. So there's all kinds of other stuff in the previous paragraph that's not shown here that probably would have been important. But you can just say C 1.3. All right, let's do a problem from this section that deals with an LR circuit. Where's the book? The book. I was looking at this one. It looks kind of weird. Not weird, but let's do a piecewise function. What the heck? Where am I going? I'm going here. All right. So this is our problem. Um, so for an LR circuit, we have the differential equation kind of given to us, and then we're asked to solve for this differential equation where L is usually constant, but sometimes, like in this case, it's not, and so we have to deal with that. I guess the only other thing we need to know is that the resistance is measured in ohms, so R is equal to 0.2. Is that right? For all you circuits people. So we have L, we have R, and we have our E. Okay, I want us to find the current I. I is the current, and so I is in the differential equation here, first order differential equation. So let's see, should we write it out? So this looks like we have to break this up into two cases when it's between 0 and 10 and when it's bigger than 10. So let's see. Yeah. So it looks like when t is less let's do bigger than 10 because it looks like it's 0. So there might be some nice things that would happen here. L of t is equal to 0. This is 10. When t is bigger than 10, L of t is equal to 0. So your differential equation is going to be not a differential equation anymore. And then so we can solve for I, right? What's I equal to? 4 divided by this. This is 2/10, right? 10 over 2. 20. So when t is bigger than 10, this turns out to be a constant. So we need to solve for the differential equation when L of t is equal to this, and that's the differential equation for t is between 0 and 10. So we have 1 minus 1/10 t times di dt is equal, nope, not equal to yet. It's plus the resistance 0.2 times I is equal to 4. Oh, what kind of a differential equation is this? Do whatever. Is it separable? All right, let's separate it. So it looks like it's separable. 4 minus what is equal to dt over 1 minus 1 t. Looks like I'm going to have a couple of logs here, right? Yeah. So I'm going to do a u substitution and divide by the coefficient. So I think it's a 1 over negative 0.2 ln of 4 minus 0.2 I on the left side. And then we have 1 over negative 1. Oh, okay, sorry. 1 minus 1 over 10t. Is that good? No. What's missing? Plus c. So the plus c placement here is kind of important. We have to make sure that we get that in the right spot. Yeah. Because it's, you know, how we're used to just saying plus c and then you leave it as a constant on the outside of e, like in the previous problems. I don't think it'll work out like that in this particular case because this is not just a regular function. It's also an ln. So having the plus c after the ln expression is important. Because if it was inside the ln expression, it's going to be incorrect. Multiply by 0.2, negative 0.2 maybe. The i's on the left side, so let's do an ln of 4 minus 0.2 I, and then let's multiply everything by 0.2 negative. So this will become positive, this will be 20, and then I don't know, t over 10, just 2. And now the constant times 0.2, it's going to be another constant, right? So I'm going to call it C sub 1. And then we'll take the ln or the e or whatever. Oh, maybe we'll get rid of this first. Let's put it as a power. So we can look at it as being squared. All right, so this is going to be 1 minus t over 10 squared, and the ln by itself, so that we can take the e of both sides. Minus 0.2i is equal to, well, it's the e of this thing. It'll be 1 minus t over 10 squared. Times e to the c, which we can call c2. It's times, right? Yeah. All right. Maybe we need some clarifying thoughts here. We're taking the e of both sides, so e of the ln of 1 minus t over 10 squared plus c is e to the ln of 1 minus t over 10 squared times e to the c, and that's why this is a times e to the c, which we can call a. All right, let's, there's an initial condition, and this works for 0 through 10, so including 0. So let's put in the initial condition. We got I of 0 is equal to 0, so I is equal to 0. And then t is equal to 0. So a is equal to what? A is equal to 4. So it's 4? Okay. And then we can solve for I. So what's I equal to? So there's a 4 over here that we can bring over to the other side. And we have to divide. Let me do this in a couple of steps, since I have to divide by decimals. So if I bring the 4 over to the other side, I have 4, 1 minus t over 10 squared minus 4. And then I divide by, multiply by 5, so that gives 20. So I of t is equal to 21 minus t over 10 squared minus. So this is a piecewise function. This is only good for going from 0 to 10. So you want your piecewise function, running out of space and time. Oh no. It's going to be this thing, 20 1 minus t over 10 squared minus 20, as long as 0, 10, and what is it before? It's 20. T bigger than 0. Well, let's graph it. So y equals, let's see, 20 1 minus x over 10 to the second power minus 20, and this is good. Oh, crap. X if 0 less than or equal to x less than 10. Haha, I'm not doing this right. And then there it goes. 20 if x is bigger than 10. So I'll replace this again. Probably did. Where? Right here? What do we want negative? This is a minus? Oh, yeah, look at that. Wow. That would change this into a minus, right? Just one of them? This is how it's supposed to look like? All right. See you guys on Tuesday. Practice. Practice.